We are going to see chronostratigraphy, and for that purpose we are going to understand geochronology. We have seen that lithostratigraphic techniques do not involve determination of the age of the rock, and the biostratigraphic techniques let us to correlate locally and regionally, and these are the oldest techniques in stratigraphy. In lithostratigraphy and in biostratigraphy, not much technological application is involved. Technological applications come in magnetostratigraphy, in chemostratigraphy, and then what we are going to do now, radiometric dating. The absolute age of the rock is obtained or minerals. Previously, the age of the earth was obtained based on the rate of evolution of species, rate of deposition of sediments, and the thermal behavior of the earth and the sun, but none of them provided accurate date of the earth. When we say the minerals can be dated, orthogenic minerals such as glauconite, green mica in some sedimentary rocks is of good use. If we date the minerals in a metamorphic rock, usually it indicates the age of the metamorphism and not the age of the original rock. When an alpha decay takes place, the parent isotope gives rise to daughter isotope and the alpha particle, which is 2He4, and when we say beta decay happens on the parent isotope, it produces a daughter isotope and the beta particle, which is electron given by beta minus. For example, 87 Rb alters to 87 Sr and beta particle is released, and 147 Sm is radioactive and it decays to 143 Nd and it releases the alpha particle, which is 2He4. We normally assume that when a mineral crystallizes out of a magma to form part of an igneous rock, there is only the parent isotope present. This is an important assumption. We do not consider that the daughter isotopes are present at that point. In other words, that is the beginning of the radiometric clock. Similarly, we assume that only the parent isotope is present when a mineral is precipitated chemically. Example of chemical precipitation can be limestone formation in shallow sedimentary environment usually, or when solid state recrystallization happens in a metamorphic rock, the radiometric clock starts. So, this is one, this is the second, and this is the third point when the radiometric clock can start. So, it looks like all the daughter isotopes measured in the rock today are formed as a result of decay. Now, here comes the change in the idea. This may not always be the case, because addition or loss of isotopes can occur during weathering, diagenesis and metamorphism. The three processes: diagenesis, whereby loose sediments become more compacted and produce sedimentary rocks; weathering, which mostly happens in the shallow crustal depth; and metamorphism can make the system open instead of a closed system, and in the open system these daughter isotopes might be lost. So, if a geochronologic dating is done on weathered rock, a rock that has undergone diagenesis in certain cases, and a metamorphosed rock, we may not get the actual age of the rock, but younger age can be obtained. How do we go for radiometric dating? Usually several kilograms of rock is collected. The inhomogeneities in the rock are removed. Samples are crushed to sand and granule size and thoroughly mixed to homogenize the material, and smaller subsamples are selected. If specific minerals to be dated, then using heavy liquids, the desired minerals can be separated. Magnetic separation can be used to separate magnetic minerals. In case of argon isotope analysis, the mineral grains are heated in vacuum and the composition of the argon gas driven off is measured directly. Measurement of the concentration of different isotopes is performed using mass spectrometer. Several micrograms of samples are heated in a vacuum in a mass spectrometer to ionize the isotopes, and these charged particles are then accelerated through a tube in a vacuum by potential difference. Radiometric dating is the only technique that can provide absolute age of rocks through stratigraphic records. Note that if the Detrital grains are dated from a sedimentary rock. For example, if orthoclase feldspar is dated from sandstone, we will not get the time of sandstone formation, rather the time when this feldspar was produced, possibly in some igneous body such as granite, will come out. So, we have to be alert. Same problem comes with mud rocks and conglomerates. So, dating of clast has to be interpreted carefully. Almost all sedimentary rocks are excluded from this method of dating and correlation. Similar problem arises with the limestone CaCO3. The mineral glauconite is an exception, which is an orthogenic mineral, forms in shallow marine environment. Glauconite contains potassium and may be dated by potassium argon or argon-argon method, but the mineral is readily altered and limited in occurrence. So, finding out glauconite is an issue. A radioactive nuclide decays to its daughter, parent decays to the daughter, and its rate of change is independent, and this is the fundamental information applied in the geochronology. Not just dating of the rock, but geochronology has allowed us to trace the origin of human culture, agriculture and civilization, and these originated more than 5,000 years back. The origin of our species to some 35 multiplied by 10 to the power 4 years, the origin of humans, the genus Homo, to more than 2 million years, and the origin of life to at least 3.5 billion years. The history of geochronology mainly starts with Rutherford's study. The basic equation of radioactive decay is given by dN dt is equal to minus lambda n. Here n stands for number of radioactive atoms, T stands for time, dN dt represents the number of atoms that undergoes radioactive decay per unit time. Lambda is known as the decay constant. We can define decay constant as the probability that a given atom would decay in some time dt. The lambda's unit is per unit time T inverse. Decay constants continue to be the field of active research. Now, if we look at 40 K producing the daughter atoms of 40 AR and 40 CA, in that case the decay constant lambda is given by 5.531 multiplied by 10 to the power minus 10 per year. 87 RB beta minus decay and is altered to 87 SR. 138 LA alters to 138 CE and 138 BA. 147 SM alters to 143 ND by alpha decay. Alpha is 2He4. 176 LU undergoes beta minus decay and it gives 176 HF. 187 RB undergoes decay and it gives 187 OS. 190 PT undergoes alpha decay and it gives 186 OS. 232 TH thorium undergoes a decay and it produces 208 PB. 235 U uranium decays to 207 PB and it undergoes alpha decay. 238 U it loses 2He4 and produces 206 PB. In all these cases the decay constants are presented. With improved research, these lambda values have been under change. So, if we look at old literature, some variation from the lambda values of these parent isotopes can be found. Now, coming back to this equation, dN dt is equal to minus lambda n, one can rearrange and undertake an integration. Dn divided by n, integration from n0 to n is equal to minus lambda dt, and here is integration from 0 to t. This means at time t equal to 0, consider n0 number of atoms were present, and at time t equal to t, n number of atoms are present. Now, on integration we get log n divided by n0 is equal to lambda t, where we have used ln log, that means to the base e. E means the exponential series. Now, this can also be written in this way: n divided by n0 equal to e to the power minus lambda t, or n is equal to N0 multiplied by e to the power minus lambda t. We are going to define half-life since we want to know the amount of time for the number of parent atoms to decrease to half the original number, that is a time when n divided by n0 is equal to half. So, if we set n divided by n0 to half, from this equation we can finally come out with t half is equal to log 2 divided by lambda. T half is the half-life, lambda is the decay constant. So, from here we can also say T half is inversely proportional to the decay constant. Consider that there are d star number of daughter isotopes produced. So, we can say that N0, the initial number of atoms, minus n at time t is equal to the number of atoms produced. So, d star is equal to N0 minus n. If we eliminate N0 from this equation and that equation, we come to this new equation, d star is equal to n multiplied by e to the power lambda t minus 1. While this is true, it is also true that in general there will be some atoms of the daughter nuclide to begin with at time t0. So, in this expression I only need to add d0 as the initial number of daughter nuclide. So, that will be equal to the d value. Earlier we have said that the d star is the number of atoms produced by disintegration. Since here this total number is not entirely due to disintegration, but because of the presence of some earlier d0, that is the reason d star is written as d. Now, this e to the power lambda t can be expanded in the E series format, and we know that lambda t is very less than 1. So, all these terms are nearly equal to 0, they are very small. Therefore, e to the power lambda t becomes equal to 1 plus lambda t. Once this substitution is made, we find d is nearly equal to d0, this much is written, plus n multiplied by lambda t. We are going to write this equation in terms of Rb to Sr decay. 87 Rb produces 87 Sr. This is the parent, that is the daughter. So, the daughter D will be equal to 87 Sr plus daughter D0 present before the disintegration started, which would be 87 Sr. 0 means at time T0 before the start of the radioactive decay, this was already present. Then plus n, n here is the parent, which is 87 Rb multiplied by e to the power lambda t minus 1. So, it is written here. So, now from the rock, if we can find out the 87 Sr concentration, 87 Sr 0 concentration, 87 Rb concentration, if we know the lambda value for this decay Rb to Sr, then we can calculate time t, the age of the rock can be obtained. But here is a problem. It is difficult to measure geochemically these amounts. Instead, what is easier to measure is 87 Sr by 86 Sr. That is why here in this equation everywhere we divide by 86 Sr. This 86 Sr is non-radiogenic, which means 86 Sr does not undergo disintegration to produce other isotopes. The rubidium-strontium dating is a widely used method to date igneous rocks because the parent element rubidium is common as a trace element in many silicate minerals. The ratio 86 Sr to 87 Sr, or if you call 87 by 86 Sr ratio, depends on the proportion in the original magma. The rubidium and strontium concentration in the rock can be measured by geochemical analytical techniques such as XRF, X-ray fluorescence. Instead of a specific mineral dating, the whole rock dating can be performed with the RB-SR method. If the igneous rock crystallizes at different times, it will contain different amounts of rubidium and strontium. Now, similar expressions can be written for other decay systems, and we can have a look at this point itself. This was the expression explained in the last slide. and in case of the SMND method, this expression holds true. Lambda 87, here instead of using lambda in this particular case, from this reference lambda 87 has been stated, which is the decay constant of 87 Rb, that is why 87 is stated. In case of SMND method of geochronologic dating, 147 SM decays to 143 ND. So, this is the parent and that is the daughter. Therefore, here 143 ND divided by 144 ND is done. 144 ND is a stable isotope, and here it is 143 ND by 144 ND at time t, at some time, which initially we were writing as time equal to 0. Here we will write the parent isotope and will be divided by 144 ND. In the previous case, division was made at both sides by 86 SR, which is a stable isotope. In case of SMND, division is made by 144 ND. This portion remains the same, e to the power lambda t minus 1, and here instead of lambda we have written lambda 147. Lambda 147 means the decay constant for 147 SM to 143 ND transformation. Samarium neodymium dating, SMND dating, SM and ND are the two rare earth elements and they are present only in parts per million in the rock. The slow generation of 143 ND means that this technique is best suited for older rocks dating, and the effects of analytical errors are less significant in this case. SMND dating technique has been used on sediments to provide information about the age of the rock. Let us take the LU-HF method. Here 176 Lu disintegrates to 176 HF, and here beta decay is involved. So, here this is the parent and that is the daughter. Now, here what do? We take the daughter 176 HF divide by 177 HF. Here 177 HF is the stable isotope of HF, and it is equal to, same thing is written at instant t, 176 HF by 177 HF plus then the parent, which is 176 Lu divided by 177 HF, and e to the power lambda t minus 1. Lambda 176 has the same kind of meaning what I explained for lambda 147 for the SMND dating method. So, in this case a division has been made by 177 HF, which is the stable isotope. Now, let us come to the REOS method, where 187 Re alters to 187 OS. This is the parent and that is the daughter. Lambda 187 has the same kind of meaning what I explained regarding lambda 147 regarding SMND dating. So, how the equation will be constructed? Here 187 OS is stated is equal to 187 OS at time t plus 187 Re, this is the parent, plus e to the power lambda 187 multiplied by t, this and the exponential series, and then minus 1. Now, here at both the sides division by 188 OS was made, and here 188 OS is a stable isotope of OS. REOS dating, rhenium-osmium dating. Rhenium overall occurs with less concentration in the rock, but the 187 Re is the most abundant isotope. It undergoes a beta decay. So, 187 does not change from rhenium to osmium. REOS technique has been used to date mainly the sulfide ore bodies and basalts. There is also some successful attempt to date mud rocks with high organic content. Earlier I have described how the strontium isotope curve can be used to have an idea about the age of the rock. Similar technique has been applied with the 187 OS divided by 188 OS ratio, because the osmium isotopes in sea water have also varied through time.